Hello and welcome to heat transfer lab. In today's experiment, we will perform heat transfer in laminar flow. This is the experimental setup. In this setup, there is a heat exchanger, double pipe heat exchanger. Also, we can say concentric tube heat exchanger. In this heat exchanger, hot fluid is sent in the inner pipe. Just so this. The hot fluid is sent through this into the inner pipe. Cold fluid is sent in the outer pipe. For the cold fluid, we use tap water. This tap water goes to the rotameter. Then it enters to the heat exchanger in the outer pipe. For the hot fluid, we use water, heated water. This is the storage tank for the hot water. Inside this tank, there is a heating coil which is used to heat up the water. This is the parallel flow heat exchanger. There is one other type which is known as counter current heat exchanger. But in our setup, this is the co-current heat exchanger. So both fluids enter from the same side. Edging for the both fluid is same on the other side. This hot fluid is circulated through the pump to the valve, then it enters the heat exchanger, then it exits from the other end, it goes to the cylinder, then in the end it goes to the storage tank again. It's a complete circuit for the hot water. For measuring the temperature, we use temperature indicator. There are 4 readings, 2 for the inlets, one for the cold water inlet, one for the hot water inlet, 2 for the outlet, one for the cold water outlet, other one is for the hot water outlet. For this, there are 4 thermocouples which measure the temperature. This is the outlet, hot water outlet. This thermocouple is for the cold water outlet. This thermocouple is for the hot water inlet, and this thermocouple is for the cold water inlet. All readings we can note down from here. And this is the controller where we set the desired temperature. Using this cylinder, we measure the volumetric flow rate for the hot fluid. The volumetric flow rate for the cold water is measured using this rotameter. And in general, we keep the flow rate above of the 100 lph. The reason is that when we keep a very small flow rate, then there will be fluctuation, and when we keep a very high flow rate, there will not be a significant temperature difference. So therefore, we keep around 100 or 120, 50 somewhere in that region. For the hot water, we measure the volumetric flow rate using this cylinder. The reason is that rotameter cannot measure the very low flow rate in the laminar region. Therefore, we use this graduated cylinder. Now come to the process. Overall process is very simple. First, we need to set the desired temperature from here. Using this screw, we can set the temperature. Right now, it is at 70 degree. We have set it at 70 degree. Once temperature reaches at the desired set value, we just open the valve for flowing the cold water. Then just start the pump from here for flowing the hot fluid. Next, we need to open the valve from here. So this hot water enters in the inner pipe, exits from the other end, it goes to the cylinder. Now it is coming. Then it will go to the storage tank. Before measuring the volumetric flow rate, it is always advised to wait for some time so that system can reach the steady state. Otherwise, due to the temperature difference, there will be some significant difference in the viscosity that can affect the flow rate. Note down the volumetric flow rate of the cold fluid. Then stop this. Note down the time until this place. Then again open this. Repeat this experiment at least 3-4 times so that you can have average value plus error. This is the hot water inlet temperature. For the hot water outlet temperature, we can measure from here T1 first reading. This is the hot water outlet temperature. Just wait for some time. Next, we need to note down the cold water inlet temperature. Then cold water outlet temperature. Alright, now we'll change the flow rate of the hot fluid. From this valve we can control the hot fluid flow rate. Again we will wait for the steady state, then we will stop this and we will note down the time up to this place. So this will be the second reading. Accordingly we will note down the all 4 temperatures. For the cold fluid, flow rate is kept constant. Similarly we will do 3-4 readings, 3-4 different flow rates we will use, and we will note down this time and all the temperatures. After that we can calculate the overall heat transfer coefficient as well as individual heat transfer coefficient for each side of the fluid. So details about the calculation we will see later. Now coming to the theory involved in the experiment heat transfer in laminar flow. Experimental part we already have seen, therefore right now we will discuss about the calculations involved in this experiment. This is the cartoon of the setup where hot fluid enters the inner pipe, cold fluid enters the outer pipe in this double pipe heat exchanger. Cold fluid, which is the water, comes from the tap, enters the rotameter, then exits from the other end, and thereafter it enters the outer pipe. Cold fluid exiting from the other end goes to the external reservoir. Hot fluid comes from the storage tank through the pump, then it goes through the valve, ultimately it enters the inner pipe of the heat exchanger. Hot fluid exiting from the other end enters the cylinder, then it exits from the other end, then goes to the storage tank again through this valve. This cylinder is used to measure the flow rate of the hot fluid, where we close this valve and then we note down the time to fill this cylinder up to the marked place. Flow rate of the cold fluid is measured using the rotameter, which is kept constant. In our experiment we kept at 150 lph. Before doing experiment we must know what we have to find from the experiment. Here in this experiment we need to find the overall heat transfer coefficient with the help of logarithmic mean temperature difference. Then we need to find the individual heat transfer coefficients with the help of overall heat transfer coefficient, and eventually we have to verify the results with the empirical equation, that is the Cedar-Tate equation. When flow is in laminar region, then Cedar-Tate equation is found useful, and when flow is in turbulent region, then Dittus-Boelter equation is found useful, especially in the case of fully developed turbulent flow. So very first we need to know the time, minimum time to fill this cylinder up to the marked place so that flow is in laminar region. For that we can use the Reynolds number concept. In the case of laminar flow, we know that Reynolds number should be below 2100 or 2000 sometimes we can see in some references. So we can use a Reynolds number for this inner pipe, DI U rho by mu Reynolds number for hot fluid flow. Di is the inner diameter of the inner pipe, which is known. The property of the fluid should be taken at the mean temperature. For example, if the inlet temperature of the hot fluid is 70 and outlet temperature of the hot fluid is 50 degree, then mean temperature will be 60 degree. So in this case, we have to give the value of viscosity and density at 60 degree. Now we need to find the velocity of the fluid inside this pipe. From here we can find the velocity of the fluid in the cylinder. Say this is UC. Velocity is distance by time. Distance is h, which is known from bottom to marked place, that is h. Thereafter we can find the volumetric flow rate. Say this is QC. Then it will be UC into AC. AC is the cross-sectional area of the cylinder. UC pi d square by 4. D is the diameter of the cylinder, which can be measured. This one. This inner diameter of the cylinder. Once we find QC, velocity inside this pipe can be found from the mass conservation principle. Mass flow rate inside this pipe, say this is mH, which will be the mass flow rate of the fluid inside this cylinder under steady state condition. Remember that. So mc is nothing but rho c rho into qc, density of the fluid and volumetric flow rate of the fluid, hot fluid, and this one is rho qh. Density is not varying much, therefore we can cancel. So qh is equal to qc. QC is nothing but this one we have already found. And UC is h by t. So h pi d square by 4 into t. And QH can be written in terms of velocity and area, U into area AH, h pi d square by 4t. U is the velocity of the fluid inside this pipe. AH is the cross-sectional area of the inner pipe in the direction of flow. So U can be written h pi d square by 4t into AH. AH is nothing but pi d I square by 4. Di is the inner diameter of inner pipe. 4 will be cancelled. Pi will be cancelled. Therefore we will have h d square by t into di square. This velocity can be put at this place. I'll write here. This one I'll put at this place. So Re di h d square rho t di square mu. 1d will be gone. So d square h rho by t di mu. Reynolds number for the laminar flow should be less than 2100. So this can be put at this place. D square h rho by t di mu less than 2100, or t should be greater than d square h rho by di mu into 2100. So time should be greater than to this value. In our calculation we find that t should be greater than 16 seconds. Minimum time to fill this cylinder up to the marked place should be at least 16 seconds. Using this valve we can control the flow rate. Accordingly we can set the time. Now coming to the calculation for overall heat transfer coefficient. For that we need to use the rate of heat transfer. Heat is transferring from hot fluid to cold fluid, this direction. So rate of heat transfer is equal to U I A I delta T Lm. Delta T Lm is the log mean temperature difference. AI is the cross sectional area in the direction of heat flow. So in this case this is the surface area. So AI pi di into L. Di is the inner diameter of inner pipe, L is the length of the inner pipe, which is known. Delta TLM can be given temperature difference at the inlet TH1 minus TC1 minus temperature difference at the outlet TH2 minus TC2 divided by ln ratio of these two. This rate of heat transfer can be found from the total heat lost by the hot fluid in a particular time. So that is nothing but minus mh cph delta t th2 minus th1 final minus initial. Here negative sign is used. The reason is that hot fluid is losing the heat, therefore we will get the negative value, and negative will be positive. This is mh dot. So mh dot can be written in terms of density and volumetric flow rate. Rho qh cph th1 minus th2. This negative symbol I have taken inside this. Volumetric flow rate inside the pipe will be the same as volumetric flow rate inside the cylinder. So rho qc cph th1 minus th2. qc is nothing but this one. cph is specific heat capacity of the hot fluid. This should be taken at the mean temperature of the hot fluid. So this one can be equated here, and from here we will get ui rho qc cph th1 minus th2 divided by ai delta t lm. Here everything is known, therefore we can find the overall heat transfer coefficient. Delta TLM from here, AI from here, CPH is the fluid property is known, QC from here, temperatures inlet and outlet of the hot fluid both are known, densities are known, therefore we can find the overall heat transfer coefficient. Similarly, when we change the flow rate, we will have different volumetric flow rate, different velocity, different volumetric flow rate. We will get different overall heat transfer coefficient. When we decrease the flow rate, time will increase. When we increase the flow rate, time will decrease. Now coming to the calculation of individual heat transfer coefficient. We know that the inverse of overall heat transfer coefficient with heat transfer area gives the total resistance. We have three resistances. One resistance exists in the inner fluid film, 1 by Hi Ai, plus conductive resistance across the solid wall, Xw by K A Lm where xw is the thickness of the pipe, inner pipe, k is the conductivity of the pipe, solid wall, alm is the log mean area of the pipe, inner pipe, and plus 1 by ho ao. This is the resistance existing in the outer surface of the inner pipe in the cold fluid film. HO is the heat transfer coefficient and AO is the surface area, outer surface area of the inner pipe. From here we can write UI is equal to 1 by HI plus XW K ALM AI plus 1 by HO AI by AO. This AI I have taken right side. AI I already have wrote pi DIL and AO. This is the area of outer surface of inner pipe. So pi DI plus XW into L should be twice X. DI plus 2XW. So up from here to here DI and thickness from both sides will be counted. So that will be 2XW. Here diameter and thickness both are fixed. Therefore AI and ALM both will be constant and also XW will be constant. At the same time here temperature difference across the wall is not very much, therefore this will not change much. So overall this one will be almost constant, conductive resistance will be constant. Now coming to this one, this area, inner area of inner pipe can be equated to the outer area of inner pipe. If thickness is very small, we can take this one. 1 by HI is equal to 1 by UI minus XW AI by K ALM minus 1 by HO. Overall heat transfer coefficient for a particular fluid flow we know. This is also known. Only we need to find the HO. Once we find this, we can find the inside film heat transfer coefficient. And we know that heat transfer coefficient depends on several parameters. For example, fluid properties such as density, viscosity, conductivity of the fluid, specific heat of the fluid, and also temperature of the fluid, temperature of the surface, and also velocity of the fluid flow. Here velocity of the cold fluid flow is kept constant and temperature difference is not very much in the cold fluid region, therefore this one will be constant, almost constant. So this one is also constant, both are constant. We can assume a single constant C and write 1 by HI is equal to 1 by UI minus C, where C is equal to this plus this. Only we need to find this one. This is known because each parameter is known. Only we need to find the HO. Once we find HO, we can find C, and thereafter we can find the HI. Next we will use Cedar-Tate equation. Nu 1.86 PR RE 1 by 3 DI by L power 1 by 3. Nu can be given with the ratio of convective heat transfer to the conductive heat transfer of the fluid. HI DI by KF. KF is the conductivity of the fluid, not solid. We are writing this expression for the hot fluid flow, which is in laminar region. 1.86. This is constant Cp mu by K F Re Di U rho by mu 1 by 3 Di by L power 1 by 3. Mu and mu will be cancelled out. Hi is equal to 1.86 di and kf I'll take in the right side. Kf di all together in one bracket, and after that u power 1 by 3. In the right side only u is changing, other parameters are almost constant, and this u is the velocity of the fluid inside this pipe, in the inner pipe. So apart from this is constant, we can consider this one constant, say C1. So HI is equal to C1 U 1 by 3, or we can take inverse, 1 by HI is equal to 1 by C1 into 1 by U 1 by 3, power 1 by 3. Some time back I wrote 1 by UI is equal to 1 by HI plus XW AI K ALM plus 1 by HO. So from here 1 by HI we can put at this place. Thereafter we will have 1 by UI, capital UI, overall heat transfer coefficient, 1 by C1, 1 by U, velocity of the hot fluid flow inside the pipe, plus C. These two we assumed constant as C. So this one I have written here. Next we can plot U power 1 by 3 and 1 by U power 1 by 3 and 1 by U. This is the inverse of overall heat transfer coefficient. This is the inverse of cubic of velocity. So this one will give a straight line. Y, this is x, so y equal to mx plus c, straight line. Intercept will give c. Once we get c, we can find HO. 1 by HO is equal to c minus this resistance XW AI by K A LM. And from here we can find HI. I'll write at this place. C we have obtained from the graph. UI we know for each flow rate. Therefore we can find heat transfer coefficient, inside film heat transfer coefficient for each flow rate. This is the experimental inside film heat transfer coefficient. So both heat transfer coefficients we found, outside film heat transfer coefficient and inside film heat transfer coefficient. This is the experimental value. We can compare this experimental value to the theoretical value. Theoretical value can be found from here. Nu can be written HI di by K, so I can write HI is equal to 1.86 into Kf by di. So using this equation we can directly find the inside film heat transfer coefficient. This is the theoretical value, where PR is known, that is Cp mu by K, Reynolds number, di u rho by mu. For each flow rate we will have velocity, and accordingly we will find heat transfer coefficient. Other parameters are almost constant. So this is the experimental HI, this is the theoretical HI. We can compare both, and also we can compare the Nusselt number. Nusselt number directly we can calculate 1.86 PR RE 1 by 3 di by L power 1 by 3. So therefore we can find the theoretical value of the Nusselt number, and this can be verified with the experimental data. Nu HI di by K Kf. So this is the experimental HI which can be plugged here, and we will get experimental value. This is the experimental, this is the theoretical. We can compare the Nusselt numbers, we can compare the heat transfer coefficient, experimental to the theoretical. So this is what we had to do. Overall heat transfer coefficient we had to find, individual heat transfer coefficient, then we had to verify the empirical equation. From the experimental result, we had to verify the empirical equation. So that's all for the today learning. I'll stop myself. And in the next lecture, we'll talk about the heat transfer in turbulent flow. Till then, bye bye and thanks for the attention.